How far will the Moon move away from the Earth? With every circumnavigation of the Earth, the Moon moves roughly 1/8 of an inch further away from the Earth. There arises the question as to whether the Moon might leave Earth's orbit altogether. Let me start with the answer to this speculation. The Moon can be viewed as a satellite of the Earth. This constellation allows us to make fairly reliable predictions regarding the final outcome. It turns out that eventually the Moon will circle the Earth at an approximately 43% slower rate, at a roughly 45% greater distance. In what follows, three simplifying but nevertheless realistic assumptions are made as follows. First assumption: the Moon is on a circular orbit around the Earth's center of mass. Actually, Earth and Moon rotate around their common center of mass. Second assumption: the Moon is treated as a mass point circling the Earth. Third assumption: the axis of Earth's rotation is perpendicular to the orbit of the Moon. Due to tidal forces, a satellite becomes tidally locked over a time period of millions of years. This means that from the surface of the central body, only one hemisphere of the satellite can be seen. Our Moon is tidally locked. Over a much greater period of time, the central body will be tidally locked as well. In this case, the satellite can be seen from only one hemisphere of the central body. Using basic laws of classical mechanics, we can infer how fast the system will rotate in the final state of full tidal locking. From a physics point of view, the formation of a state of full tidal locking is a process where angular momentum is transferred from one body to another, but the total angular momentum of the system is conserved. This would be the formula for computing the total angular momentum of the system in its present state. This is for Earth's rotation. Due to its dense core, the moment of inertia for Earth's rotation cannot be easily computed. This should be a quite accurate estimate. This part is for the angular momentum of the Moon. As indicated, the Moon is treated as a mass point. Here numbers have been filled in, and here is the result of the computation of the total angular momentum of the system. For satellites orbiting the Earth, orbital radius and angular velocity omega are not independent. The gravitational force acts as centripetal force. We can write this. From this we obtain something that corresponds to Kepler's third law. Here we have again the formula for the total angular momentum of the system. Here is the value computed for the present state of the system. The formula contains the orbital radius and two angular velocities, omega m and omega e. Here the orbital radius is being substituted, and the resulting equation has two angular velocities, omega m and omega e. Once full tidal locking has been reached, we only have one angular velocity. This equation therefore contains only one unknown, the angular velocity omega of the system. Substituting numerical values, we obtain this equation for omega. Here the equation has been rewritten twice. This equation can be solved with suitable software. The value obtained for omega is 1.52 times 10 to the minus 6 seconds to the minus 1. From the computed angular velocity, we can compute the length of a sideric day once full tidal locking has been reached. One can see that days would last roughly 48 times longer than now. Using the formula corresponding to Kepler's third law, we can compute the orbital radius of the Moon for full tidal locking. One can see that the distance of the Moon would increase by roughly 45%. This is quite minor compared to the dramatic slowdown of the rotation of the Earth.